A very good evening to Dr. Zamri. We are here to present about our assignment 2, which is the real-time messaging with Apache Kafka in KRaft mode. My name is Hokaing, number metric 293256.
And my name is Phang, number metric 293084. Background: Apache Kafka is a popular tool for real-time messaging. It is reliable and scalable. Previously, Kafka needs Zookeeper to manage cluster. Now, with KRaft mode, Zookeeper is no longer needed. This makes Kafka simple to set up and use. Using Docker to set up Kafka also make it easy and consistent across systems.
Problem statement wise, nowadays achieving fast, reliable, and scalable communication between distributed systems is a critical challenge in today's data-driven world. So Kafka is here to help us by distributing streaming platform, which can be used for building real-time data pipelines and streaming apps. It's a highly scalable, fault-tolerant distributed system.
The main objectives are to develop a Java program that uses Kafka in KRaft mode with Docker to enable real-time messaging between two PC, to integrate the Open Weather API to fetch and include weather data in the message, to demonstrate how Kafka provides fast and reliable communications. Methodology. First, we set up Docker and Docker Compose on both PC and ensure they are on the same network. Next, we configure Kafka in KRaft mode using Docker Compose, eliminating the need of Zookeeper. We then create the producer program on PC1 to send weather data from the Open Weather API to Kafka and creating a topic for the message. On PC2, we develop the consumer program to listen to this topic and display the received message. After that, we test communication by running the producer and consumer to verify the message are sent and received correctly. Finally, we manually fetch weather data from the Open Weather API to verify the integration accuracy. Result: the system works for real-time messaging, where messages sent from the producer are received by the consumer with low delay. This message includes weather data fetched from the Open Weather API, showing that Kafka can handle real-time API integration well. This proves that Kafka in KRaft mode and Docker is effective for messaging between systems. This architecture uses Apache Kafka and Docker to send weather data from the Open Weather API. The system consists of three parts: the producer, Kafka topic, and consumer. The producer fetch weather data from the API and send it to a Kafka topic. Kafka store the data in the topic, allowing the producer and consumer to operate independently. The consumer will read and display the data. Docker run all components to ensure the system is easy to deploy, scale, and maintain. In short, the producer fetch the data, Kafka send it, the consumer display it, and Docker ensures smooth operations. This is the weather producer Java code, which acts as a Kafka producer. It sends real-time weather data to the weather topic. We have set the Bootstrap server IP follow the producer IP address. This section configures the Kafka producer, including specifying the Kafka broker address and setting the serializers for the key and value. This section sends a GET request to the Open Weather Map API to fetch weather data for a specific location. In this case, we use London. After a successfully response, weather data is passed into a JSON object and sent to Kafka. The Kafka producer is then closed to release resource after the data have been sent.
Next, we'll be having the weather consumer file. Basically, the skeleton will be as same as producer file, where we have the topic, weather topic, the bootstrap server, which is the IP address of producer, and also the group ID, which is weather group, to ensure that we are in the same group ID. And then we'll be having the properties, which is the IP address, the group ID, the key and value deserializer, which it converts the message into Java, which is into string. And then the consumer will subscribe to the topic and ensures that it's single topic subscription. And last, we'll be having a loop where the consumer will update the data for every 100 milliseconds. And at last, print the message in console using printf.
The wait for Kafka script ensure Kafka is up and running before starting the producer application. The set-e command ensures the script stops if any command fails, preventing further execution in case of an error. The script checks if Kafka is accessible on port 9092 using netcat. If Kafka is unavailable, it prints a message and waits for 5 seconds and retries. Once Kafka is ready, it prints a message indicating that the Kafka is up and then execute the Java producer applications. This is the POM XML from the producer side. The Kafka client dependency is included to enable the Kafka producer to send message to a Kafka topic. The main class is set to weather producer to ensure the application runs the weather producer class.
For the POM XML for consumer, the main class is set to myUUM weather consumer. At the Docker compose YML file, we will be having the port number 9092 as the default port number for communication between producer and consumer. Next, we have the 29092 as the Kafka internal communication. We also have the IP address of producer at both PC and also a 20-second timeout to avoid unhealthy situation. For the Docker file, we uses OpenJDK 24 SimBullI as our Docker. We are using the same OpenJDK.
Now moving to the demonstration process section. On the producer side, we first enter the docker compose down command to stop the currently running container. Then we use the docker compose out build command to start the Docker container again. The same steps are followed on the consumer side. We type the docker compose down command to stop it. And then docker compose up build to start it again. After the consumer side finished running, it displays Kafka server started. Next, on the producer side, we go to Docker and run the producer container. When we click the run button, user terminal shows the output, which means the weather message is sent. On the consumer side, the terminal displays the weather message. If we click run again on the producer side, the producer terminal shows another message, indicating that the weather message is sent. And the consumer side displays the weather message again. On the consumer Docker terminal, the same message is displayed. To verify that the message sent and received really fetches from the API, we copy the link URL. Replace the API key and location with London and paste it into the browser. The result confirms that the weather message matches. In conclusion, this project shows that Apache Kafka in KRaft mode is a strong tool for real-time messaging. Using Docker makes the setup simple. Fetching data from the Open Weather API and including it in the message show how Kafka can work with external API. This method is good for building applications that need fast and reliable data sharing.
Last but not least, this is our reference use. The top three were the one that we used to do our problem statement, while the third until the 10th are the one that we use to develop our project.
That's all for our presentations. Thank you.